Bismillahirrahmanirrahim. Dear students, I hope that all of you will be fine. And today's our topic is the conservation of electric charge. First of all, electric charge is something possessed by a material object, by means of which electrical and related effects are observed within that object. Now after that, this electric word comes from this Greek word electron. This electron, it means amber. So amber material, if rubbed with wool, it gets electrified. Means a net amount of electrical charge is acquired on amber. Due to this meaning, we can use this electric word. Electric word used as a prefix in many physical quantities such as electrical force, electrical charge, just like electric power, just like as the word electricity. So this word has the origin as amber. After that, this electric charge is conserved. Means in universe, I will state in this way, in universe the net quantity of electric charge. In universe, net quantity of electric charge remains constant. Net quantity of electric charge that is constant, that remains constant, that is conserved, or I may say just like this, in a closed system. In a closed system, net amount of electric charge, net charge remains constant. Its value not changes. That we know, that means constant, that means conservation. Or I may say just like this, if we have a system, I will take this as system, closed system or an isolated system. If within this system some amount of charge is lost within this part, then the same quantity of charge will appear in its any other part. For example, if we have a body, that body gains an amount of charge plus Q, then that means there in surroundings is another body which loses an equivalent amount, means that loses an amount of minus Q, and that is now gained by this system due to this within this body and its surroundings, the total charge remains conserved. Or we can say in this way, the net quantity of charge in a closed system that always remains constant. So again, this electric charge can neither be created nor destroyed. It can transfer from one body to another body. The overall charge of the two interacting bodies that again remains constant. So these are the some of ways by means of which we can state this law of conservation of electric charge. Now I will take some examples so as to explain this law of conservation of electric charge. First of all, we know that its origin is from an atom. If we have an atom, that atom is composed of protons. They are positive in charge. After that, these are composed even of neutrons. They we know their charge is neutral. After that, these electrons, their charge is negative. For example, I will take this atom, carbon 6, this one, 12 as isotope. So within this we know there are 6 protons and there are 6 electrons. So the total amount of charge which is present within this carbon atom, that is equal to 0 in its isolated state, because we know this proton is having a charge of 1.6 into 10 raised to the power minus 19 coulomb. After that, this is having the same magnitude of charge, however that is negative, means 1.6 into 10 raised to the power minus 19 coulomb. So total charge within this atom If this one is not ionized combined with anything, then its charge is equal to 0. We know if we have an element such as any metal, I can take this is a metal. If this loses an electron or one or more electron, for example, this loses an electron. So this reaction occurs when this loses n electrons, its number of protons, for example, if they are equal to Z. Within this, the number of protons, they are equal to number of electrons within this. After that, there are now Z number of protons and the number of electrons, that is equal to Z minus n is less than this. For example, if I will take this equal to 10, then this equal to, if the number of electrons they are equal to 2, for example 2 electrons are lost by this element, then the number of electrons within this will be equal to 10 minus 2, so that is equal to 8. Now these are positively charged, means here is plus 10, after that there is this one, they are negatively charged minus 8, so there remains plus 2 charge. Plus 2 charge means it now acquires a charge. It becomes positively charged. Why it becomes positively charged? That is due to loss of electron. Similarly, any body becomes as negatively charged when that body actually gains one or more electrons. So this electronic charge means E equal to 1.6 into 10 raised to the power minus 19 coulomb. This one is regarded as a natural unit of electric charge. So charge on proton, that is positive, charge on electron, that is negative. Now we know we have even more elementary particles, but those elementary particles, they are now believed to be, they are even smaller than this, they are fractional of this charge. However, the concept remains same. But these elementary particles, according to this quark model, we can say these elementary particles are even made up of even smaller elementary particles. We call those as quarks. And those quarks, when they combine, they will again hold these elementary particles, means electrons, protons, and neutrons. That model even leads to this, and we will restrict ourselves to this, that materials, matter is composed of electrons, protons and neutrons. Now a substance acquires positive charge when it loses one or more electron. After that it acquires negative charge when it gains one or more electron. That was the same as performed by Greeks. For example, I will take this example. If we have a glass rod, for example, I will take this as glass rod. If that is rubbed with silicon, this one, I will take the material, I will take the piece of silicon. If these two are rubbed, then upon rubbing, this one also electrified, this one also electrified, this glass rod becomes positively charged and this one becomes negatively charged. Whatever is the amount of positive charge produced within glass, that is exactly equal to amount of negative charge developed on silicon. For example, this one acquires a positive charge of plus Q. Then the negative charge obtained by silicon, that is equal to minus Q. Overall, I may say the net electrical charge within this, means glass rod and silicon system, that again is a constant quantity, that is equal to 0. Means they are again neutral if combined, or I may say the charge present on these two bodies, that first before rubbing that is equal to 0, now after rubbing that is again equal to 0. So in case of electrical phenomena, again the net charge before any interaction is equal to net charge after that interaction, means this charge remains constant. Now I will take this example, I will take some nuclear reactions here again. This one as this nuclear fission reaction, uranium-92, here I will take this 235 when bombarded with a neutron. This one has neutron, so it first of all gets converted into uranium-92. After that, here 236. This one being unstable, we know this superlattice, this breaks down into lighter nuclei, into smaller nuclei. They are in one of the fission processes, barium and krypton. For example, here I will write it is atomic number 56, it is atomic number 36. Now within this reaction, I will write here 3 neutrons. These are the nuclei. So we know nuclei are positively charged. The positive charge on this side, that is equal to positive charge on this side, on the reactant side, that is equal to 92 plus 0 into charge on one proton. Charge on one proton, I will take that equal to E. I will take that positive charge equal to 92 E. E is the magnitude of charge on proton. Now on this side of the reaction, 56 plus this one 36 plus here again 3 into 0, that is equal to 0, that is again equal to 92 E. So within this reaction again the charge on the left side, that is charge of reactant, is equal to charge of product. So in case of any nuclear reaction, again this charge remains constant. After that I will take this reaction. For example, we have this beryllium, it is atomic number we know 4, I will take it as mass number 9. So this isotope, if bombarded by means of this alpha particle is having this notation. So these two, when they will combine, they will form this isotope of carbon. C I will take here 12. After that I will take this one as 0 and 1. Now within this reaction again 4 plus 2, that is equal to 6 E. Now here again 6 plus 0, that is equal to 6, means 6 E amount of charge, 6 into charge on proton that is present on right side of the reaction, that is same equal to charge that is present on left side of the reaction. So within this reaction, we know this is the reaction used for the discovery of neutron. Within this reaction, we have obtained this particle, means this neutral particle that we call as neutron. This is the reaction carried out by James Chadwick for the discovery of neutron. So within this reaction, again charge on left side, that is equal to charge on right side. So whether we will take any chemical reaction or we will take any type of interaction between two bodies, for example, if these are the two bodies in my hands, if they will interact with each other, if positive charge is obtained on this, positive charge is acquired by this object, then the equivalent amount of negative charge is acquired by this object. Overall, we are sum this plus this, that is again neutral. In a similar way, in universe, we commonly, as per our experience, we know the net charge in the universe that may be 0. So if in any part of the universe charge appears, then the same amount of charge disappears in its any other part. Now I will take some properties of electric charge. Only main properties, I will discuss them briefly. So properties of electric charge. First of all, charges are of two types. We call one as positive charge, another one as negative charge. This positive charge is obtained, is acquired by a material by losing one or more electrons. This one losing one or more electrons. After that, negative charge is acquired by an object, by a material that is acquired if that object gains one or more electrons. Gains electrons. After that, if these two charges, we have two charges, for example, one charge as plus Q, after that this charge as minus Q. if brought close to each other, they will attract with each other. Means unlike charges attract each other. After that, if we will bring two similar charges close to each other, then they will repel each other. Means this one, if minus q, here minus q, they are brought close to each other, they will repel each other. I can say like charges repel and unlike charges attract each other. So this is the one property of electrical charge. After that, I will mention this. Electrical charge is quantized. Electric charge is quantized. This quantization concept of electric charge applicable at the microscopic level. I can say just like this. Electric charge is also made up of discrete units. Discrete units in the sense charge present on any body. Suppose we have a body, charge present on that body is equal to Q. Then that will be equal to plus minus this n. N means a number, that number we can take equal to 0, 1, 2 and so on. This one means this E, charge on proton or charge of an electron, that is the natural, that is the elementary unit of charge. Charge possessed by any object, that is integral multiple of charge of electron or charge of proton. We know this quantization charge, it has been experimentally verified by Faraday's laws of electrolysis. I can say within them we can explain this quantization of electric charge, Faraday's laws of electrolysis. After that, we know Millikan's oil drop experiment also confirms the quantization of electric charge. So there are many experiments by means of this. At microscopic level, we can say there occurs quantization of electric charge. That again I will say, if we have a body, then this body is having charge. For example, if on this body, if there is plus 2 charge, that is again equal to integral multiple. For example, I will take here 10 into charge on electron or charge on proton. This one 1.6 into 10 raised to power minus 19 coulomb. So anybody, if that is charged, then on that there may be either positive charge or negative charge. That charge is equal to integral multiple of charge on electron if negatively charged, equal to integral multiple of charge of proton if positively charged. So this one being the basic unit, natural unit, elementary unit of electric charge. I will take some calculations regarding to electrical charge. For example, we know electric charge is having SI unit that we call as coulomb. So C is the SI unit of electric charge. Now 1 coulomb of charge, how many electrons are present within 1 coulomb of charge? We will use this equation. Q is equal to plus minus Ne, means quantization of electric charge. Here this one means we have to calculate here number of electrons that will constitute 1 coulomb of charge. So Q is equal to 1 coulomb. After that, E we know that is equal to 1.6 into 10 raised to power minus 19 coulomb. So within this equation, N is equal to Q divided by E. That is equal to 1 coulomb. After that, this one E 1.6 into 10 raised to power minus 19. So this is equal to 0.625 into 10 raised to power plus 19. This one is the number of, or I may say just like this, 1 coulomb of charge is approximately equal to charge on 10 raised to power 19 electrons. So this is a bigger amount of charge. such amount of charge possessed by 10 raised power 19 electrons constitutes 1 coulomb of charge. After that, I will now move towards this point. If this body, for example, we have a body that ejects electrons, that releases electrons, from this electrons are transferred. Suppose the number of electrons which are ejected by this body, they are equal to 10 raised power 9 per second. Number of electrons ejected by this body, they are equal to 10 raised power 9 electrons per second. Now, if such an amount of charge is released, such a number of electrons are ejected by this body, they are coming from this body, how much time it will take to accumulate a charge of 1 coulomb? Means if the electrons from this body, they are in number 1 billion per second. If that number is accumulated, how much time it will take to accumulate 1 coulomb of charge? Now again here I will take this number of electrons. They are equal to number of electrons, that is equal to 10 raised power 9. After that, charge on electron, that is equal to 1.6 into 10 raised power minus 19 coulomb. Negative charge, so we have to determine here only magnitude. First of all, charge on one electron is equal to this. Now charge on n electrons is equal to Ne. That means 10 raised power 9 into 1.6 into 10 raised power minus 19. That is equal to 1.6 into 10 raised power 10 minus 10. This one is the charge in coulombs possessed by 10 raised power 9 electrons. So total amount of charge possessed by electrons which are emitted per second, which are released per second, that is equal to 1.6 into 10 raised power minus 10 coulomb. Now this is the charge released per second. Now we will convert this in years. For example, this one 1.6 into 10 raised power minus 10 coulomb. After that, this one 365. After that, 24 hours. This one 60 minutes into 60 seconds. That calculation is simply equal to nearly, this will be the time in years. This is the charge released by these electrons per second. So this one in years, time in years. That is now equal to, if we carry out this calculation, that is approximately equal to 200 years. That means if electrons are emitted by a body, they are released by a body, they are leaving a body at this rate. Means 1 billion electrons are releasing a body or leaving a body per second, then that will take a time of approximately equal to 200 years to accumulate 1 coulomb of charge. Now it seems that for practical purposes, many practical purposes, this 1 coulomb of charge or coulomb of charge is a bigger unit. So we can use now smaller units. For practical purposes, we may use these units. For example, microcoulomb. Microcoulomb, this one is equal to 10 raised power minus 6 coulomb. Or we may use this nanocoulomb of charge, that is equal to 10 raised power minus 9 coulomb. Or we may use this picocoulomb of charge, that is equal to 10 raised power minus 12 coulomb of charge. So these are the some smaller units of electrons.